Hello everyone and welcome back. My name is Mr. Kovalt, and in this video I'm going to be going over the equilibrium constant and the reaction quotient. So let's get into this. So when we're talking about the equilibrium of a reaction, one of the questions we want to ask ourselves is the product or the reactant favored in the reaction? Well, what does that mean to be favored, right? So once an equilibrium is reached, you're either going to have more products present, or you're going to have more reactants present, or they're going to be equal, right? It's usually not the case that they're equal. So you're either going to have more of the product or less of the reactant, and less in the reactant, or you're going to have more reactant and less product. In that case, we say the reaction is favoring the products or the reactants. So if you end up at equilibrium and you have more reactants than products, like as in this picture here, right? So if this is at equilibrium, and at equilibrium, my amount of reactants, the concentration or amount of reactants at equilibrium is more than that at products, then the reaction is favoring the reactants, meaning that it prefers to have the more reactants than products. Oops. Sorry about that. So, what about a product favored reaction? So, if a reaction favors products, then in that case, at equilibrium, you're going to have more product compared to reactants. So, here we have more products compared to reactants, and it's at equilibrium. So, this would be a products favored reaction. It prefers to have more of the product than the reactants. And so that's what we mean by a product favored or a reactant favored reaction. So, how does this relate to the equilibrium constant or the reaction quotient? Well, it deals with ratios. So, if you remember from a previous video or a couple videos back, um, you'll see that, or you'll remember that I talked about the reaction, the equilibrium constant, and how the constant is a ratio, and it's a ratio of products over reactants, or products to reactants. And so in this case, if we were to take the amount of our products here for our reactant favored reaction, if we take the amount of products and put that over the amount of reactants, we have a smaller amount of products, so that's going to be on the top, and a larger amount of reactants that's going to be on the bottom. So our denominator is going to be large, and our numerator is going to be small. So in that case, your equilibrium constant is going to be small because you have a large denominator and small numerator. And so that's going to make the fraction, the ratio is going to be small. So your constant, your equilibrium constant is small. In a product favored reaction, uh, if you remember that the reaction, the equilibrium constant is products over reactants. If you take this here, we have a large amount of products, put it over a smaller amount of reactants, then our ratio is going to be large over small. So the ratio is going to be larger. So our reaction, our equilibrium constant is going to be a large number. So that's just like, if you can think about that or imagine that using the pictures and the amounts, that's basically how they're related. And that's what we mean by reaction favored, reactant favored versus product favored. So let me get into the KEQ and talk about the law of mass action in just a moment. Okay, so let's start with a simplified version of this. So again, the question is product or reactant favored? And so we saw just a moment ago that you can understand the KQ, or what side is favored, based on what side of your equation, reactants or products, you have more of at equilibrium. And how does this relate to the KEQ, or the equilibrium constant? Well, KEQ is a value, it has no units, that allows us to determine if more products or reactants are being made. So if you are given the KEQ or the K of a reaction or a reversible reaction, that will tell you if more products are if products are favored, meaning you have more products at equilibrium, or if reactants are favored, meaning you have more reactants at equilibrium. And so, as I said earlier, a simplified version of KEQ is that you have the concentration of products over the concentration of reactants. So KEQ is essentially equal to that ratio. So it's the ratio of concentration of products over reactants. And so you can get a picture here of how you can use K to determine if products or reactants are more prevalent or more in abundance at equilibrium. So if K is large, then that means that this ratio is large. So that means that you're going to have more products on the top and less reactants on the bottom. That's going to give you the large number. So your denominator is going to be small and your numerator is going to be large. So that's going to give you a large K. So if you have an equilibrium constant that is large, then or above 1, then that means that you're going to have more products, and products are favored at the equilibrium for this reaction. If K is smaller or less than 1, right? If K is small or less than 1, that means that you have less products in the numerator and more reactants in the denominator, thus making the ratio small. So if you get a K that is less than 1, then you're going to have more reactants, and that means reactants are favored in the reaction. So that's how KEQ, or the equilibrium constant, is related to the concentrations of products and reactants. And so next I want to talk about the law of mass action and talk about how we can use that to get a version or more complicated version of the KEQ expression that's going to allow us to calculate what the equilibrium constant is for various kinds of equilibrium or reversible reactions. Okay, let's talk about the law of mass action now. So, the law of mass action basically says that the rate of a reaction is going to be proportional to the concentrations of its reactants, right? So, in this case, we have a forward and backwards reaction. Oops. Sorry about that. So in this, whenever we have an equilibrium, we have a forwards and backwards reaction. So the reactants here are going to be the concentration of these reactants are going to be proportional to the rate. The rate of this forward reaction is going to be proportional to these. And the backwards reaction, these are going to be the reactants, so it's proportional to those. So when we have an equilibrium, we have to consider the concentrations for all of these when we're talking about the rates of the reactions. And we said it before that the rate of at equilibrium, the rate of the forward reaction is equal to the rate of the reverse. So when all of this is taken into consideration, the KEQ is going to involve the concentrations of all four of these. So the way we do this, and remember before, it's the ratio of the products over the reactants. So what's the form of KEQ, the expression of KEQ, given this equilibrium, generic equilibrium here? Well, the small letters are the coefficients in front of each of the substances, your products and reactants. And the capital letters represent the substances. So when you write the expression for KEQ for your reaction, it's always going to be products, concentration of products over reactants, and it's the concentration of the products raised to the power of their coefficient. So here I have a coefficient small c, so I have the concentration of big C raised to the power of small c. So if this is a 1, then this is a 1. If this is a 3, then this is a 3, right? And then same thing with this product too. So it's going to be multiplied. So you're multiplying the concentrations of the products and each product is raised to the power of their coefficient. So this is small d and that's small d. So if this is a 2, then that would be a 2 power squared, right? And then on the bottom, we would be dividing by the concentrations of our reactants. So it would be the concentration of the reactant multiplied by the concentration of the other reactant, and each of these would be raised to the power of their respective coefficients. And that is how you write the expression for KEQ for any reaction. So one thing to remember, so remember from previous video that solids and liquids don't factor into the equilibrium, and that is because they don't really have a concentration that's going to go into this equation. This equation has concentrations. Gases can have a sort of concentration to them, so we could fit gases in there. And of course, things that are aqueous are going to have concentrations. But solids and liquids don't really have a concentration that we can really fit into this formula or this equation. Or if they do have a concentration, it really is constant. So we don't really have a change in here. So it's not going to be added. Okay. So a word about this KEQ being unitless. Now you may think or wonder yourself, well, how can KEQ be unitless if we're multiplying and dividing by the concentrations, and we measure concentration in molarity, right? So if these coefficients aren't equal on both sides of our equation, then it's not going to all cancel out. So how can it not have a unit? Well, the reason there, really quickly, is that, and it's not shown in here, and we usually ignore it, but when you're putting in your concentrations, you're not just putting in the concentration, you're putting it in a concentration as a ratio to a standard. And the standard here is 1 molar. So when you put in the concentration of your substance, it's going to be a ratio of that concentration over 1 molar. So for example, here, if I have if the concentration of A is 0.2 molar, then I'm going to add it to the equation in this form here, 0.2 molar over 1 molar. 1 molar is the standard. And then you'll notice that the molarities cancel out. And so these values that we're putting into our equation here don't have any units. So the molarity units are canceling out because we're writing them in the relationship to 1 molar, the standard here. And so the same thing also applies to gases and pressures in atmospheres. So anytime you're giving a partial pressure to a gas, that's going to be in atmospheres. And then so you are relating that to the standard, which is 1 atmosphere. So the atmospheres end up canceling out as well. And so you don't have any units. Okay, so that's why KEQ is unitless. I just wanted to go over that, just clarify that in case that was a question. Okay, let's go over a practice problem and see how this works. Okay, so let's go over this problem. So we're asked to write the equilibrium constant expression for the reaction. So they want KEQ. So we got to remember that according to the law of mass action, KEQ is going to be equal to the concentration of products raised to their coefficients divided by the concentrations of reactants multiplied and raised to their coefficients. So if we write the generic form again, that would be, so the products over reactants, so it would be C raised to the C power multiplied by the concentration of D raised to the D power over the concentration of A raised to the A power, and then that is also multiplied by the concentration of B raised to the B power. And so this is generic form. So if we apply this to our equation here, then we write K EQ or just K, KEQ and K, same thing. So KEQ is equal to, and then we're going to have products over reactants. So we have two products. So it'll be the concentration of NO. So we have the concentration of NO, and then there's a coefficient 2, so we're going to raise that to the second power. So that's going to be raised to 2 or squared. And then we have our other product, that's oxygen, so we're going to multiply that by the concentration of O2. And then since there's a coefficient 1 there, then this is raised to the power of 1. We don't write the ones, but it's there. So now we have our products done. And so now our reactants are going to go on the bottom. We only have one reactant, so it's going to be the concentration of NO2. And we have a 2 coefficient, so that means it's going to raise to the second power. So here it's going to be a 2. And there you have it. So this is the equilibrium constant expression, the KEQ. And so that's how you do it. And it's no harder than that. So let's move on to our reaction quotient. So, but before we get to our reaction quotient, I have one more thing that I want to talk about. Now, we wrote the KEQ for the forward reaction because we have products over reactants. Well, what if they want the KEQ or the equilibrium constant for the backwards reaction? Well, in that case, the products become reactants and the reactants become products. So you just reverse this equation and write that KEQ like that. So in that case, we would have this on our product side. So if I write that really quick, so here you'll have 2NO gas plus O2 gas in equilibrium with 2NO2 gas. Right, so there's our reverse reaction. So the KEQ for this would be concentration of NO2 squared, because we have a 2 there, so raising that to the second power. And then we have 2NO, so it's going to be the concentration of NO raised to the second power because we have a 2, multiplied by the concentration of oxygen to the 1 power. So we have a 1 coefficient here, 1. So that would be the KEQ for the reverse reaction. Now, notice here that the relationship between the KEQ for the reverse reaction and that of the forward reaction, oops, I'm looking here. So this is the forward reaction. This is the forward and reverse or backwards reaction. What do you notice about them? They're reciprocals of each other. So if you find one, you just flip it and you get the other one, right? So the K of the reverse, I'll say REV for reverse. The K of the reverse is equal to 1 over the K of the forward. I'll just put 4 for forward. So 1 is the reciprocal of the other. So if you want to find the K for the reverse reaction, you just flip these and you'll get the KEQ for the reverse. And that's what happens here. So I hope that was helpful. And so now we'll go on to the reaction quotient. Okay, I tricked you again. So not quite getting to the reaction quotient. One more thing I want to cover is what about pressures? What if I have pressure and not concentration? Well, the great thing about that is you just use the partial pressures the same way you use concentrations. So here you have your generic equation. So here's your KEQ expression, and it's exactly the same with the one we saw before with concentrations. However, in this one, we're using partial pressures. So it would be, again, it's going to be the pressures, the partial pressures of the products over the partial pressures of the reactants, all of them raised to the coefficient, raised to the power of their coefficient. So here I would have the pressure of substance C raised to the C power. And again, this would be in atmospheres, but it's going to be unitless. KEQ is unitless because, again, the atmospheres cancel out because the partial pressures are being related to a standard pressure of 1 atmosphere. So the units cancel out and keep the numbers. So here we have the partial pressure of substance C raised to the C power, and then multiplied by the partial pressure of substance D raised to the D power. And then all that is divided by the partial pressure of A raised to the A power and the partial pressure of B raised to the B power. So exactly same form, except instead of concentrations, you are using partial pressures. Now, another thing I want to point out is just to let you know that a lot of times, if we are using concentration, we'll refer to KEQ as K sub C for concentration. So when we're using concentrations, you might see K in this symbolism here. So using K sub C instead of KEQ means the same thing. So when we're using partial pressures, we might represent KEQ as KP. So KC, equilibrium constant for concentrations, and then Kp is the equilibrium constant for when we are using pressures or partial pressures of our substances. So I just want to throw that in there just in case you see that symbolism as well. Okay, now let's get into the reaction quotient. This time, I mean it. Okay, let's now talk about the reaction quotient. So, what if you're given a problem or you're given a situation where you're not sure if the reaction is at equilibrium or not? Well, how can you tell? Well, what you would do is take the information of the values and the concentrations of the substances they gave you and plug it into your K expression like you normally would, and then compare that value with a given KEQ value that they're going to give you. You need the KEQ value in order to determine whether or not you are at equilibrium with the concentrations that they are giving you. So, so if you are not at equilibrium, which means that your value that you got is not equal to KEQ, then the value you got, we call that the reaction quotient, or Q. And so the expression for Q is exactly the same expression for KEQ, or K, right? So here's our generic equation. Here's our expression for Q. It's, again, according to the law of mass action, we're going to add the concentrations of our products over the concentration of our reactants. And so we have the concentration of C raised to the C power, concentration of D raised to the D power, concentration of A and concentration of B raised to their respective powers on the bottom. And so what you would do is, in the problem, they're going to give you a set of concentrations. So you take those concentrations of your products and reactants, plug them into your expression here, which is exactly the same expression for K, and you calculate your reaction quotient Q. And then you see, is Q equal to the KEQ that they give you? If it's not equal to KEQ that they give you, then your reaction is not at equilibrium. If it is equal to the KEQ that they give you, then it is at equilibrium. And so that's how you can tell. So again, the only difference between Q and K is that Q is for substances or reactants that are not at their equilibrium concentrations, right? So that's Q. And then if your reaction concentrations, if the substances are at their equilibrium concentrations, then that is going to be K. Okay, so that's the only difference between Q and K. Q is for concentrations not at equilibrium. K is for concentrations that are at equilibrium. So let's talk a little bit about how we can use K to figure out which direction is the reaction going to move. Is it going to move to the right? Is it going to move to the left? Do we have more products than we need, or do we have more reactants than we need? Right? So let's get into that next. Okay, so really quickly, so what does Q tell us? Well, if our Q value is equal to K, then you're at equilibrium. So everything's good. However, if your calculated Q value is larger than K, then that means you have too much product. And remember, the ratio is product over reactants. So if Q has a larger amount of product, so that's going to be large Q compared to K. So this means that the reaction is going to have to shift left until you make enough reactants in order to get back to equilibrium. So it's going to shift towards the left to make more reactants. If your Q value is smaller than K, then that tells you have too much reactant, and reactants are in the bottom, right? So that's going to make Q smaller than K, and that means that the reaction is going to have to shift to the right to make more product, and then it's going to do that until you make enough product to get back to equilibrium. So that's what Q will tell us compared to K. So remember these. So why do we care about KEQ so much? Or let's talk about that next. Okay, so why do we care about KEQ? Well, if we know KEQ, this will allow us to solve for a couple of things. For example, one, it would be able to solve for which combinations of concentrations would reach an equilibrium position. So what concentrations would we need to get to equilibrium? So we could solve for that. The other thing we could solve for is whether or not the given concentrations that we have are at an equilibrium point. And we can do that by comparing Q to K, right? As we just saw, if Q is larger than K, then that means that we have too much product. And so it's going to have to shift towards the reactants to lose product and create more reactants, right? So we can figure that out. If Q is smaller than K, that means we have too much reactant and not enough product. So it's going to have to shift towards the products in order to get rid of the reactant and create more product. And so, but if we K and Q are equal to each other, then we know our reaction is at equilibrium with those concentrations. So knowing K is valuable in being able to do those things. So that's it for this part of the video. So in the next part, I'm going to do a practice problem and go over, excuse me, go over a few things that we need to remember about what is going to affect K and what things don't affect K. So I hope this video was helpful. If you enjoyed this video, if you like this video, if you learned anything from this video, then please like the video, hit that like button there, share the video with your friends. Also, make sure you subscribe to my channel, hit that notification bell. When you do, make sure you hit all so you can be notified by all the videos I put out. And then finally, put a comment down below in the comment section. Let me know what you think. And if you've got any questions, I would love to hear from you. Thanks for joining me and have a great day.